So I welcome all the participants for this session 2 of day 5 in STTP on applied computational fluid dynamics for engineers, organized by Mechanical Engineering Department, AD Patel Institute of Technology, a Constituent Engineering College of CVM University. So our session expert, Dr. Anil Date sir, is joined with us. Now I'll request Dr. Mitesh Shah sir, guest. Over to Mitesh Shah sir.
Very good morning to all the participants and our speaker, and very warm welcome to Professor Date sir for giving his valuable time in spite of his age, and not only the age but online platform. That is very difficult task for the aged person. And then also he has committed and he shown his interest to address us in computational fluid dynamics. Before we start this session, I would like to introduce him. Professor Date obtained his B in Mechanical Engineering from VJTI, Bombay University, MSc in Thermofluids from University of Manchester, Institute of Science and Technology. He did his PhD, DIC, in heat transfer from Imperial College of Science and Technology, London University in 1973. Professor Date joined Mechanical Engineering Department of IIT Bombay in August 1973. So quite senior professor, very legendary personality. As a member of the thermofluid group, he has made extensive contributions in convective heat and mass transfer and computational fluid dynamics. Professor Date has published over 100 papers in national and international journals and conferences. He has carried out research consultancy projects for government and industries. He has also held a biotechnology development through his associations with the Center for Technology Alternatives for Rural Areas in IIT Bombay. Professor Date has held visiting scientist cum professor assignments in Cornell University, UIUC, University of Karlsruhe, Swiss Federal Institute, Zurich, City University, Hong Kong, and NAL at Bangalore. He has given seminar in Australia, Hong Kong, China, Germany, Sweden, UK, USA, as well as in IITs, NITs, and RECs. Professor Date was elected Fellow of the Indian National Academy of Engineering in 2000. He received Excellence in Teaching Award of IIT Bombay in 2006. In 2009, Professor Date was chosen to be the first Rahul Bajaj Chair Professor in Mechanical Engineering by IIT Bombay. He was appointed as Emeritus Fellow of IIT Bombay during 2010 to 2013. In 2012, Professor Date received the Lifetime Achievement Award of IIT Bombay for outstanding performance, outstanding contributions in teaching, research, and administrations. Presently, Professor Date is an honorary professor in Mechanical Engineering Department of IIT Bombay. Sir, we are really happy and fortunate people to listen you at this age, and I am very much happy to show that you are at this age showing your interest and delivering and addressing to the faculties of across the country. Thank you very much, sir. I request you to share your presentations and start.
Yeah?
Yes, sir, your presentation is visible.
Yes. Can you hear me?
Yeah.
Okay. Thank you, Professor Shah, for such a kind introduction. Whenever I encounter a person who is a Shah or a Patel, I feel like speaking in Gujarati, but today I'll refrain from doing so. And I'll quickly move to the topic of the day, and that is demarcating laminar to turbulent transition, range of Reynolds numbers, in ducted helical flows using low turbulence Reynolds number form of K epsilon model of turbulence. Case of applied CFD to track information of fundamental interest. I say this because this is a seminar for engineers, and if you ask any engineer, does it really matter to you whether the flow was laminar, transitional, or turbulent? And he says, no, it wouldn't, as long as I know what the pressure drop is and the heat transfer is. But as you will see on the next slide, I'll be referring to Osborne-Reynolds in a short while, but the order of my presentation is as follows. I have divided my lecture in 3 parts. Part 1 is transition in a straight tube of circular cross-section. Part 2 is CFD prediction of transition in a tube with a twisted tape insert. Now this is a helical flow, and the transition phenomenon is very special. It is different from what you see in a straight tube. And I want to explore that through CFD. And then I shall be presenting 2 unresolved problems for which they are both helical ducted flows, for which we have experimental data, but they need to be validated through CFD, and they pose a lot of CFD challenges, which I'm sure your august audience would be able to appreciate. So let me go to the next slide. Yes, so I start with the part 1, and I start with recalling everybody's memory that the very first paper on transition was actually presented by no other than Osborne-Reynolds on the dynamical theory of incompressible viscous fluids and the determination of the criterion. The criterion here he is talking about is when laminate flow becomes sinusoidal. And it is published in Philosophical Transactions of the Royal Society in 1895. Now, of course, something more about Osborne-Reynolds. Since this is a seminar on engineering, let me say that Osborne-Reynolds was the first full professor of engineering in UK, and the English like to think that anywhere in the world. But the second thing that I would like to refer to is the year 1968. That was the year in which Osborne-Reynolds was appointed professor in Manchester in 1868. And 1968 was celebrated as the Osborne-Reynolds centenary year. And as part of that, they had an open day in Manchester University. And I, being a student at that time on the MSc course in Thermal and Fluids Engineering, along with my fellow students, was asked to monitor this experimental setup which was put up there by Manchester University. And it was an open day, so school children would keep coming, and they would be absolutely thrilled to see a flow under laminar condition where the ink dye would simply enter and leave the depth unperturbed. So to see laminar flow was itself great excitement for school children. Subsequently, of course, as you increase the flow, the dye would begin to smear, and then at a substantially higher Reynolds number, it would turn into sinus, or what Osborne Reynolds called the sinusoidal motion. And he had detected that this transition would take place anywhere between 1900 and 2000. So, for all of you, this Osborne Reynolds is a well-known figure, and I thought I should begin with him. And he was the first professor of engineering anywhere. And yet, he looked at fundamentals. Another way of looking, the modern way of looking at transition is, of course, to measure F and NU characteristics in a ducted flow, not by fluid flow visualization, but by measuring friction factor and Nusselt number. And as you can see, up to about 2000, the friction factor is 16 by Reynolds, and you have an exact solution for this. And by about 3000 or so, or 4000, the turbulent flow begins, and there is an abrupt change. So we all of us associate transition with an abrupt change in friction factor. The change is not only in the trend itself during the transitional Reynolds number, the friction factor actually increases with Reynolds number rather than decreasing as it would in a laminar and fully turbulent region. Likewise, in turbulent flow, in heat transfer, you know that in laminar flow, the Nusselt number would be constant depending on the boundary conditions. But in turbulent flow, it would begin to change with the Reynolds number. This peculiar behavior, of course, again, up to 2000, you see measurements are constant. And then from about 3 or 3,500 onwards, you get separation of with respect to Prandtl number. Now, it is very interesting to see that while in the laminar flow, Nusselt number differs depending on the boundary condition. In turbulent flow, there is hardly any effect of the boundary condition on the measured Nusselt number. Now, it is in itself a very interesting point to discuss in turbulence modeling, but I'll leave it at that at the moment. But bear in mind the definitions of friction factor and Nusselt number that we normally use. They are based on hydraulic diameter here. But in case of circular tube, of course, as you know, hydraulic diameter is nothing but the diameter itself. The next slide. The third method of measuring, of detecting transition in tube was actually used by Jesse Rota in 1956 in Germany. And what he did was to use a hot wire anemometer and placed it inside the tube facing the flow at a fixed point. Now, the fixed point may be at the axis or it may be closer to the wall, whichever way you like. But what was interesting was the following. He kept the hot wire for a long enough time and then recorded the trace of the measured velocity, and then he split the time up into equal intervals of delta t. And then he found in certain intervals there would be a burst or unsteadiness over a time delta t sub t, and that's the burst time within a interval, predetermined interval delta t. And like that, he went on adding them in n intervals and divided that by n. And of course, predictably, this quantity would be a ratio and varying between 0 and 1. And that quantity he called as intermittancy. It tells you the time for which the flow was turbulent. Of course, gamma varies with R and X, but gamma also varies with the actual distance X of the tube. This is a figure probably not often seen by academics, And it shows that the intermittency value is actually a function of x by b. And I have shown here x by d of 100, 200, 300, 400, 500. Of course, these are very long tubes, deliberately so chosen. Industrial tubes are not that long. But you will see at 2300, the intermittency varies from, let's say, less than 0.1 to, let's say, something like 0.2 itself. The surmise here is that if the tube was really very long, intermittency would approach 1, and the flow will become fully turbulent. But of course, no real tube is that long. At 2400, it reaches about 0.4 at x by d of 500. At 2500, it reaches about 0.6. At 2600, it reaches nearly 1 in x by d of 500. Now, of course, if the Reynolds number was 5000, you will get intermittency would start from 0 and reach almost 1 in less than x by d of 20. So for Reynolds number greater than 5000, the flow will be fully turbulent right from entrance, almost right from entrance. And it will remain so throughout the tube. And that's why we say in a ducted flow, the flow once turbulent, always turbulent throughout the length. This work was done by J.C. Rota, and you can read about it it's in German, but you can read about it in a book by Listing, The Boundary Layer Theory. Now, of course, the fourth method for detecting transition would be, of course, our friend CFD. And one way in which that can be done is by invoking what is called the low Reynolds number of low turbulence Reynolds number model of kinetic energy and dissipation, first introduced by Jones and Launder at Imperial College. And strangely, the model was actually introduced to predict relaminarization of a turbulent boundary layer. You know, in a highly accelerated flow, the boundary layer would be turbulent to start with, but then because of the very high acceleration, it will go on thinning, and ultimately it will become so thin that it is almost all completely located in the viscous sublayer. And that phenomenon was known as relaminarization in those, and they succeeded in predicting that phenomenon using low Reynolds number model of turbulence. Here, the proposition is the reverse. How does laminar flow become turbulent? That is number one. And instead of an external boundary layer, I'm going to look at the entrance region of a circular tube. How does laminar flow in a tube become turbulent? So I've chosen an axial length of 100 diameter and radius 1, that is the domain of computation, and two-dimensional elliptic equations for U, V, and pressure and temperature are solved with equation for kinetic energy of turbulence and dissipation rate. Now, of course, I'm assuming that you know all these equations because you've already undergone so many lectures on turbulence, on CFD. And I then obtained several solutions from as low as 500 to almost 30,000. But here I'm going to present for 1,000 to 10,000 and for Prandtl number 0.7. See the next slide. Sorry, but see the next slide, and I'll show you now turbulence model. This is the most important point that you must note is what I've said here. The turbulence model that is K and dissipation rate model, was kept alive at very low Reynolds numbers as well as very high levels throughout the entire range, laminar as well as turbulent range of Reynolds numbers. Next slide. And this is what I predicted. So these are several discrete solutions plotted on a single graph. starting with Reynolds number 1000 and going up to 10,000. So let us first of all look at U over U bar, and you can see multiplied by 10, of course, and you can see it is showing value of 20 here at Reynolds number of 1000 at U, in spite of the fact that turbulence model is active, because the model itself predicts zero turbulent viscosity, and therefore for all practical purposes, the flow behaves like it's laminar. And you will see the value remains constant at 2 U max by U bar, is that U center line by U bar remains at 2, which is the exact solution everybody is familiar with. But at something happens at, this is the value of 2000, something happens at about 2300, and the peak value begins to decline, and declines very sharply at about 3000. And from there on, it declines very gradually, and at 10,000, it reaches a value about 1.3, very characteristic of turbulent flow, where the velocity profiles are very flat. Yes, so U max by U bar is 1.3. Likewise, you will see the friction factor is F by 16. You will see this is the value of 16 here, and F by 16 is being predicted by about 400, whatever you want to say here, and then it becomes turbulent at about 3000, and then begins to follow the trend of the turbulent flow for friction factor. And likewise, the Nusselt number is, as you can see, this is 987,654 and 3. So this is a constant wall temperature case, 3.66 in the laminar range, and then it suddenly jumps and the turbulence profile. So what do I conclude from this? The CFD solutions, firstly, show that the onset is 2300, which means below 2300, the flow will be definitely laminar. And the end of transition is about 3000, which means beyond 3000, the flow will be turbulent. How vigorously turbulent is another matter, but it will be certainly turbulent. And then the second thing is, we find is that the low Reynolds number model succeeds in predicting the laminar range very well as it predicts the turbulent range. So it's a wonderful workhorse to have in locating effects of Reynolds numbers. Now here I am presenting radial profiles in wall coordinates. As you know, U plus is U over U tau, as you will very well know. So this is the profile predicted at 3000, which is the start of transition. And you will be surprised to know that actually the turbulent, the laminar sublayer up to Y plus a third, almost up to 10, Y plus of 10, Y plus of 5 is, you know, it is U plus equal to Y plus, but then it begins to change up to 10 or 11.6, and then a fully turbulent flow begins. So that is the specification of universal law 2.5 lny plus 5.5, and you see that at 3000 it is not vigorously turbulent. The core of the flow is still not vigorously turbulent. Finally, the value of RET, that is mu p by mu, of course, which will vary low with radius, and you see it is almost 0 in the sublayer region, and it goes on increasing to about 7. It goes on increasing to about 7. It goes, so right at the center line, it is no more than 7. RET max by mu t by mu max is about 6 at center line. That's the maximum value it attains at 3,000. At 10,000, on the other hand, it attains a value, it has stopped a little earlier, but it goes up to almost 50. Now, turbulent max, RET max is 50. Now you will see that the turbulent flight is much better predicted, but still it is not vigorously turbulent at 10,000, and perhaps beyond 10,000, you will get a perfect match with this. So, what I'm suggesting here is that RET max could well be a very good discriminator of transition Reynolds numbers when you are using low Reynolds number model of turbulence. So summary is the following. So transition range of Reynolds numbers can be estimated in 4 ways, by flow visualization, from intermittancy distribution, from gross F and NU characteristics, and use of CFD using low Reynolds number model. And tentative broad agreement among all methods is that for Reynolds number 2,300, the flow is definitely laminar. For Reynolds number greater than 5,000, the flow is definitely turbulent. And RET max, on the other hand, is definitely less than 10 in laminar flow, and RET max is definitely greater than 50 or 100 in turbulent flow. Now I begin with part 2, in which I do CFD prediction of transition in a tube with a twisted tape. And you can see that there is a tube with a twisted tape inside. It is spanning the diameter of the tube, and it has a thickness delta. The tape has a thickness delta, and the dimension h has very special significance. The h is the distance for 180-degree rotation of the tape, and therefore you will see, apart from the Reynolds number, h divided by diameter as well as delta divided by diameter are additional parameters influencing friction factor as well as heat transfer. So let's see. So now the question that I ask is, which among the 4 methods can be used to estimate transition? So I think it is very obvious that dye method will not work, because the flow will be, the dye will smudge even during laminar flow. Second thing, intermittency may perhaps help, but presence of flow can disturb the flow in a variety of ways, and therefore that will also not work. But measured F and NU data, yes, that can really help. That can really help to detect transition because of sudden abruptness if we show. And then finally the CFD. We can also do CFD. So we now converge on the idea that measured F data and CFD are 2 possible candidates to detect transition range in helical flow. Now here is the, as I said, friction factor would be function of Reynolds, Y, and delta star. Y is the H by D ratio, and delta star is the delta by D ratio. So here is a measured friction. Here is a definition of friction factor, functional, and I will not refer to the heat transfer at the moment. Now, I want you to pay careful attention to this figure from a paper by Manglik and Burgos, who did extensive measurements both of laminar and turbulent flow in tube with a twisted tape. And what do you see? Here is our usual friction factor plotted with Reynolds number. You can readily identify this line as that in a tube without a twisted tape. This line corresponds to y equal to infinity. You will see when this length is infinite, and therefore h by d is infinite, it essentially implies a straight tape, and therefore the duct is simply divided into 2 straight semicircular ducts. And of course, because of the additional surface area offered by the tape, you have increase in friction factor both in laminar flow as well as in turbulent flow. But then you impart twist to the tape, And here, the data that I plotted here, that are taken from paper by Mangic and Burgess, is for y equal to 3. That is, the pitch for 180-degree rotation is 3 times the value of the diameter. And their tape had a thickness of 5% of diameter. And they measured from Reynolds number 300 to almost 30,000. And also they measured heat factor. And what do you see here on the friction factor? Can you detect transition through abrupt change? No, you cannot. At 2000, there is nothing is happening. There is no transition visible except for a little bump here, which can be easily put down to a scatter. But there is no clear abrupt change in slope as associated with empty tube or with a straight semicircular duct. Now that poses a question. That means the gross features do not help in locating transition in a helical flow. So one of the things that they did to correlate this data was they generated a laminar flow correlation, they generated a turbulent flow correlation for F, and they raised, these are the correlations, I won't spend time on this, and they raised the laminar flow correlation to the factor of 10 and 10, and raised the sum of that to the 0.1, and they found the following, that the resulting correlation predicts the data over entire range excellent within plus minus 10%. The most notably, they found that there is a number called the swirl number, Reynolds the square root of y plus this quantity, and that was a number they introduced, and they said it's a very effective way of collapsing friction factor data. So one of the things that they surmised was after the core was that end of transition occurs at end of laminar flow occurs at 1400 and start of fully turbulent flow at 10,000. This you will appreciate shortly, but our present approach is, this was the conclusion they drew from their F correlation, that this correlation ceases at about Reynolds number of 1400, and beyond Reynolds number of 10⁴, the correlation is dominated by F turbulence. So our present approach is, of course, the CFD approach, and of course, since the flow is three-dimensional, one tries to simplify this thing by adopting a rotating coordinate system. So what is the rotating coordinate system? It's a coordinate system x1, x2, and it keeps on rotating with the as the tape rotates at different axial directions. The fixed coordinate system, of course, is x and y, so that remains fixed in space, and x3 coincides with z. So the rotating coordinate system goes like this: x1 will be x cos alpha plus y sin alpha, x2 would be y cos alpha minus x sin alpha, and x3 would be z, and alpha is pi z by x. It's a fraction of pi that is taken by z. So the consequence of this is, of course, d by dx would get translated to d by dx1 and d by dx2. Likewise, d by dy would get translated to d by dx1 and d by dx2. And d by dz would get translated to x1 and x2 derivatives as well as x3 derivative. Now, this is very interesting. And then, but the transformations are, of course, valid for any value of alpha. And see the next slide. what we are going to do is we are going to take alpha equal to 2 pi. So what would then happen is that sine alpha will go to 0, cos alpha will go to 1, and you will see that d by dx would be replaced by d by dx1, d by dy would be replaced by d by dx2, and most importantly, d by dx3, that is the derivative in x3 direction at constant x1 and x2 would be 0 for all variables as it is, since it's a fully developed plot. And d by dz would be this. I mean, d by dx3 will be 0, as you can see here. D by dx3 will be 0 for all variables, but this part will still remain. So the actual derivative appears in the form of transform derivatives of x1 and x2 with pi by h as a multiplier. All right. So what you do then is you look at your standard equations for u, v, w, k, and epsilon in 3 dimensions. Transform all derivatives of d by dx, d by dy, and d by dz in the manner shown here, and then simply drop all d by dx3 derivatives to 0 in respect of all variables, except of course pressure, where the pressure itself is written as mean pressure P bar x3 and P naught x1 x2, which is the local variation of pressure over the cross section. So dp dz then becomes pi by h dp naught by dx1 plus dp dot minus x1 dp naught by dx2 plus dp by dx3, which is a constant to be whose value is provided by the analyst. Similarly, something about temperature, which is obvious. Now, what you get as a result after transformation are equations like this, with u1, the convective transport velocity is u plus a component of the w velocity, u2 velocity is v plus a component of w, and then there are these derivatives that are there that appear in the momentum equations. This is the kinetic energy equation, and this is the dissipation equation. Now, the definitions of epsilon and epsilon star I give on the next slide. You can see mu t is the turbulent viscosity. Usually you will see in higher ensemble forms, you have C mu, rho mu, k square by epsilon, but here it is attenuated by another factor F mu. G is the production term. F mu is sensitized to the value of turbulence Reynolds number. As you can see that turbulence Reynolds number increases from wall, which is 0 at the wall, to as you go away from the wall, it goes on increasing, and therefore this factor goes on decreasing, and F mu ultimately disappears to 1 when the flow is fully turbulent. Epsilon star is given by this value, so it is different from our standard epsilon, and it is attenuated. Now these two terms, F mu and this, essentially make the turbulence model independent of requiring knowledge of distance from the wall. All these terms are in terms of dynamic variables, and therefore you don't need distance from the wall. Unlike in mixing length, where you need to know the distance from the wall to specify turbulent viscosity. All these are the factors I need not spend time on, but except to show that terms like phi v, which occurs in phi v, which occurs in production term, and E star are extremely long terms, and their discretization can be very, very demanding. plus the fact that there are derivatives with respect to x1 are further taken, second derivatives with respect to z, and that means this term actually has 4 terms in it. When squared, it becomes even more terms. So this evaluation of this in a in a CFD is very, very demanding for I equal to 1, 2, and 3, all 3 are to do. The most important factor is that here you don't have to give boundary condition away from the wall. You can go right down to the wall and specify kinetic energy and epsilon star at the wall as 0. This is the most advantageous, beneficial effect, beneficial aspect of using a low turbulence Reynolds number model, that all boundary conditions are very, very easy to give. And therefore, we adopted this model for throwing a tube with it, only solve the problem on the one half of the tube, that is semicircle, and we created using ANSYS the grid and the semicircular domain, so 37,000 quadrilateral elements, nearly 60 cells normal to the tube and tape wall. As you can see, this thick dark region that you see, that is what is required by the low Reynolds turbulence model. And n plus, that is the value of y plus, normal to all the walls, was always found to be less than 1.2 at all the Reynolds numbers considered. Solution requires specification of rho and mu, the fluid properties, and the mean axial pressure gradient. So if you wanted to change Reynolds number, you can change either rho mu or you can change dp by dx. In our case, we always change dp bar by dx, kept rho and mu constant. We use simple algorithm with P naught determined using smoothing pressure correction. This is an unstructured mesh, as you can see. And then from the solution, you evaluate W bar, the mean axial velocity, by integrating the profile over the cross section, and then evaluate friction factor from knowing the input value of dp bar by dx3 and now the evaluated value of W bar. So here are comparison of computed F data with experiment. Now these are the experimental data of Manglik and Burgers, and as I said, they found that Swirl number is a very good unifier of friction factor versus Reynolds number data. Friction factor multiplied by Reynolds number for swirl, suffix swirl is the usual friction factor multiplied by Reynolds number divided by this factor of y. And this is a very good unifier of all the discrete data for range of y 3, 4.56, and going from almost from as you said, what was the range in the earlier? Here from, what was the range they used? Yeah, from as low as 100 to nearly, what is here? 30,000. 100 to 30,000. So you can see that this data is the measured data. Our computations have been for y equal to 3, 6, 10, and of course infinity you have that the straight semicircular duct where the constant value that is predicted. So you can see here, this is the value 15.617 multiplied by this factor square, and that comes to about 46 point something. And then you can see our data are also predicting same trend as predicted here. So for 100, you see it is almost equal to that for semicircular tube. You can see this is converging so. At 1,000, the FRE score value is something like 80. Is it 80? At 1,000, it is something like 80. Here also at 1000, you will see our value is somewhere around 80. And at 10,000, our predicted value is something like 30 or 35. Same thing here at 30 or 35. So broadly, one can say that gross characteristics are verified. And second verification is that the numerical data also seem to suggest that swirl number is a very good unifier of twisted tape generated F data. But then we looked at the value of RET max and plotted it for Reynolds against Reynolds number. And you see the following, that this is the RET max of 10. And it shows that up to about Reynolds number of almost 4,000, you can say almost 4,000, the RET max is less than 10. But then it suddenly jumps to something like 80 and 100 at a very high Reynolds numbers of the order of 10,000 and more. It is even bigger than that. So on the other hand, if you plot RET max versus swirl, RET max data does not unify with swirl, although friction factor data does. RET max data is not unifying, and therefore it cannot be used to correlate RET max. But what it does confirm is that for swirl number less than 1400, so let's say this is about 1000 and this will be about 1400, all F data are less than 10. RET max data, all RET max data are less than 10, which we said is a good indicator of laminar flow. And for Reynolds number greater than 10,000, here, RET max is greater than 100, So we generally find agreement with the articulation of Manzik and Burgers, who said that for swirl number less than 1400, the flow is definitely laminar, and for Reynolds number greater than 10,000, the flow is definitely turbulent. And these figures essentially suggest that we could well use RET max as a discriminator of laminar and turbulent flow regions. Here are some profiles of at y equal to 3. This is the profile of W star, that is the axial velocity, and this is the profile of RET, and you can see the maximum values are occurring near the center. So I won't discuss this because the figure is not very good, very. So summary, like the flow in a plain circular tube, the fully developed flow in a tube containing a twisted tape can be effectively predicted by invoking low turbulence Reynolds number model over the entire range of Reynolds numbers for 500 to 30,000 and 3 to 10. This is the typical range used in industry, but even tighter twists have also been made. Identification of transition with 10 to 100 shows that the Dutch Reynolds number 6,000 to 9,000 is a much clearer discriminator of transition range irrespective of the value of y. Now this is interesting that in helical flow, twisted tape flow, one can surmise that the start of transition will be somewhere around Reynolds number of 6,000. That is much higher than that in a circular tube. And probably the primary reason for it is that the secondary flow creates centrifugal force, which keeps the founder layers very thin near the wall, and it takes time. It takes a much higher Reynolds number for them to burst into turbulence. And so that is the reason why probably a higher Reynolds number has been. This has also been observed experimentally by, not observed, but actually surmised by some Japanese researchers who said, and Russian researchers, who say that in swirling flow, you should have transition at a higher Reynolds number than in a straight ducted flow. Right. So for swirl less than 1400, the flow is definitely laminar irrespective of value of y, as concluded by Manglik and Berger. All right. So now I want to present to you the part 3, where there are two problems. The first is a square tube with twisted tape in it. As you can see here, again, h is the distance for 180-degree variation. But there is something very special. There's something unlike what happens in a circular tube. This tape, when it rotates, it begins to lose contact with the wall. As you can see at a certain angle, phi, it has already lost contact with the wall. And at 45 degrees, it will have a very big gap between the edge of the tape and this. So actually, quite a few observations are important. Flow now becomes fully developed over a distance of 2h. That is, the cross sections replicate themselves exactly over a distance of 2h, and therefore a fully developed flow would reproduce itself at every 2h distance. Flow cross section changes with xt. At every actual distance, the cross section is now going to differ. Unlike in circular tube, coordinate transformation is therefore not possible. Yes, because the outer section goes on. Because the direct cross section goes on changing, a simple coordinate transformation is not possible. So what do we do then? Now here are some typical domains which I'm trying to show. Here is the one for theta equal to 45. You see the tape has ended here. And here is something for, so the gap increases or decreases with the angle. And you can see that the flow here is a mirror image of the flow here. Is that right? So these are now, you have not only the flow is not only actually periodic, but the flow is also periodic at every cross section. Now these are unique boundary conditions that one must learn to apply. Now here are the measured fully developed flow friction factor. As I said, these are all measured over distance 2h. And this is the first figure is for y equal to infinity, which means it's a straight duct. So you have essentially two rectangular ducts going straight, and the measured friction factor data does show a clear departure in friction factor around Reynolds number of, let's say, about 2000 or 1800, and the rise in friction factor followed by a fall. But the moment you introduce twist, this is y of 10.26, you see there is no identification of transition abruptness. There is no abruptness anywhere at any Reynolds number. Same thing with 5.62, and same thing with y equal to 3.14. So one of the things is, one generalization one can make is that this kind of behavior was seen in a circular tube, and now it is being seen in a square tube. So is there something very special about helical flows that they do not demonstrate transitions to abruptness. Yes. So you will see abrupt transition at y equal to infinity, but near continuous variation of y less than a helical flow. This is very special feature of helical flows, that they do not transit abruptly from laminar to turbulent. So the problems are the following: how to implement low RET model, because remember you have to generate spine grids near the tape wall as well as near the duct wall, and the duct cross section goes on changing. How to provide large number of grid elements close to the tape and the duct surface? Should one use curvilinear grids or unstructured grids? And how to succeed in implementing axially and circumferentially periodic boundary conditions for scalar as well as turbulent variables. Now, this is, although I am suggesting here RET model, for low RET model, the high RET model was implemented by Ray and Date, and the paper published is IJHMT volume 46 in 2012. So, I have now turned to second challenging problem, and that is the flow in a spirally grooved tube with and without twisted tape insert. So this picture that you see here is a 75 start internally grooved tube, and we measured friction factor and Reynolds number, friction factor and Nusselt number for flow in this tube. The work was reported by Bharadwaj, Thonge and Date in the year 2009 in IJHMT. At any cross section, what you would see is a rib like this of height epsilon. All these dimensions are comparable with the thickness of the tube, by the way. And you have the tip thickness, TP, and you have the base thickness of the protrusion. The dimensions are given here. The internal diameter is 14.8 millimeters, and the length of the tube is 1040, and the helix angle with respect to the with respect to the axis, helix angle with respect to the axis is 23 degrees. The length of the tube is almost 1 meter. Incidentally, this tube, a 75 start tube, which means there are 75 grooves along the circumference. It is called 75 start tube, was supplied to us by Blue Star Limited in Mumbai, which is something as engineers we should be interested. And what did we find? So when we did measurements without twisted tape, the friction factor showed this is the smooth tube data, but you can see the helical groove tube data, the friction factor is higher than the smooth tube data. And strangely, it is showing a transition at around 2000 and say 600, so a slightly delayed transition. And then the flow behaves like a turbulent flow up to about Reynolds number of, let's say, 9,000 or something like that. But after that, you see the friction factor becomes constant, which is very characteristic of a rough tube, as you all remember. What it shows is that the swirl flow generated by the rib is now no longer effective, and the actual momentum at high Reynolds number is so high that it simply kills the effects of any flow that might be there because of the roughness, because of the ribs. But the ribs now begin to appear like a rough surface, protrusions in a tube, and therefore you see the friction factor assumes and you will see we have been succeeded in modeling it like a rough tube of roughness epsilon, roughness P that I have shown here. So this is the roughness IP, and we were able to correlate the data in this manner. There is no Reynolds number dependence, as you can see here. Then the heat transfer data again showed a little transition around 3,000. This is then smooth tube data. But in laminar flow, again, the heat transfer is high because of the helical swirl flow introduced by the spiral drift. And then this is the turbulent flow. But then there is the rough tube, which is very characteristic again, higher than the turbulent flow correlation for a smooth tube. And therefore, it suggests the very plausible trend of data throughout the range of Reynolds numbers or method number. Then we introduced twisted tapes. Now our spiral tube, the spirals were running clockwise with respect to the flow direction. And we introduced in this tube twisted tapes, both twisting clockwise as well as twisting anti-clockwise in the direction of the flow. And what do we find? We find that there is no observed departure in behavior in presence of twisted tape for both clockwise and anti-clockwise rotating tape. In fact, at very low twist of 10, there is a difference between clockwise and anti-clockwise twist, but at higher twist, the data completely merge into each other. But the only departure that you can really see is somewhere here around number of say 6,000 or 7,000, where the friction factor becomes constant, which means even in the presence of twisted tape, the flow is behaving like a rough tube, Same thing with heat transfer. Again, I did not mention that. So what do we conclude then? In summary, a tube without twisted tape, that is a spiral tube without twisted tape, both F and NU data show two transitions. First transition is from laminar-like to turbulent, and the second transition is from turbulent to fully rough tube. Now, how to represent low RET model on the smallest domain in the presence of circumferentially periodic boundaries? So do you remember this? So this is the typical cross-section of and you need not, of course, generate grid for the entire cross-section. You can take only a sector like this one, very narrow sector, and this planes passing through the tip of the duct of the rib would be not symmetric, but they will be periodic because of the helicity of the spiral. So my second is how to implement low RET model on the smallest domain in the presence of circumferential periodic boundaries. How to construct helically transforming coordinate systems. So something like a spiral, and should curvilinear or unstructured grid be used? That's because I asked that question because you have a singularity of a center of the tube. So which would be a good way of generate curvilinear grids, or both can be done or unstructured. Now in tube with twisted tape, you will have two semicircular cross sections, but whose surface has number of grooves on it. And you cannot identify a region like this one in that case. So you have to map the entire semicircular tube wall. So clockwise twisting tape in the flow direction aids the swirl flow generated by the spiral groove. Reverse is the case with anti-clockwise tape. In both cases, abruptness of F and NU data typically associated with laminar turbulent transition is absent, but turbulent to rough tube transitions are pronounced for all values of I. Can low RET model succeed in predicting such transitions? Thank you. So what shall I do now?
Thank you, sir, for your presentation. Now, I would like to ask to the participants to ask your query, please.
I hope I kept to the time. Yes, it's 1 o'clock. Good. So I think there are no questions. That means I have presented it so well that everybody is spellbound. Right. So thank you very much for inviting me, and I thank all the invited speakers and other participants for joining this program, which is very good. That the CFD is now getting known in engineering colleges, and I of course see from time to time in journals also excellent papers coming from engineering colleges.
Sir, we have maintained this practice throughout this STTP, that let us, if any participant have any query at a later stage, they may send their to me, and I'll compile it and will send it to you through mail, sir.
Hopefully I can answer this, guys. Okay. All right.
And with this, I would like to thank Dr. Anil Date, sir, and I'll thank them as per his busy schedule, with some of his personal stuff, but still on my request, he accepted it to bless us with his session.
Yeah, I wish you all very well. Yes.
We are so grateful to have you, sir.
Yes.
Esteemed personality.
And now with huge computing power available, I think we should do much better than what we could do. So.
Thank you, sir. Thank you so much. Stay healthy. Thank you so much. Yeah. Have a nice day.
Yeah.
So now I'll send a link. This is for the session 2. Session 3 will start sharp at 3 p.m.